Here's a couple of examples finding the null space and the column space of a matrix. Starting with the first example here, find the null space of this matrix A. So just to review quickly what the null space of a matrix is, by definition, it's just the solution set to the equation AX equals 0. So all we do to find the null space is solve this equation. So I skipped a few steps here. We can write them down real quick. If we have AX equals 0, we would augment the matrix A with the 0 vector and row reduce that, and we would get something augmented with the 0 vector still. In this case, the 0 vector is just the 0 vector in R3, 0, 0, 0. So, as we usually do when we're solving homogeneous systems like this, I did not augment A with the 0 vector. So I just took A here and row reduced it, and it row reduces to this form. And so I write down the corresponding system, which is here. And I've got x1 plus 2x2 plus 3x4 equals 0. That's from the first row here. And then the second row gives me x3 plus x4 equals 0. I solve for the basic variables in terms of the free variables. x2 and x4 are free here. So I solve for x1 and x3 in terms of x2 and x4, and I write down the corresponding vector equation. So here's our vector equation, and I get x equals x2 times this vector minus 2, 1, 0, 0, plus x4 times this vector 0, 0, minus 1, 1. So I get my parametric solution in the standard form. We could call it SU plus TV, where U and V are the given vectors, and S and T are in R. And so remember, the null space is the solution set. So this thing right here is not the null space. This is a vector equation. So the null space is a set. So here's our null space. Notice that the null space of A is not just equal to the set containing these two vectors, U and V. It's the span of that set. That's really important. You've got to have span on there because the span of the set and the set are two very different things. The span of the set containing U and V is not the same as the set containing U and V. So remember, the span contains all the vectors that are linear combinations of U and V. This has two vectors in it, this set. This set, the span, has infinitely many. Okay, so here's our answer. Here's the null space, the span of that set. Okay, for our second example, we want to find a basis for the column space. Notice that word there, basis. That's really important. We want to find a basis for the column space. And A is the same matrix that we were using in the first example. So if the word basis were not here, if I just wanted to find the column space, that would be really easy. By definition, the column space is the span of the columns of the matrix. So here's the column space. I could write that down without any calculations. But I want to find a basis for the column space. And that's generally what we want to know. Remember, a basis is the smallest spanning set for a given subspace. So that's what we're looking for in this case. We're going to use a theorem that says the pivot columns of the matrix form a basis for the column space. So if you want to find a basis, just find those pivot columns. So we row reduce A. We get the same row reduced form we got in the first example, and we can see here's our pivots. One there and one there. So column 1 and column 3 are my pivot columns. Now I have to be careful to use the pivot columns of A, not the pivot columns of this row reduced matrix here. If I call this matrix, say, B, A and B are not equal to each other. So I need to use the pivot columns of A, not the pivot columns of B. Well, the pivot columns of A are the same column numbers as the pivot columns of B, because A and B are row equivalent. So it's column 1 and 3 of A that will be my pivot columns. And so here's my basis. It's just the set containing those columns. Notice in this example, we are not looking for the entire column space, so we don't take the span of the basis. So when finding the null space, we take the span of the basis. If we jump back to the other example here, this set is a basis for the null space of A. Now, we didn't prove that it's a spanning set, but we didn't prove that it's linearly independent set. There is a theorem that says that, but the null space itself is the span of the basis. When we're looking for the basis for the column space, we want just the basis. So this basis has two vectors in it. Over here, the null space, which is the span of the basis, has infinitely many vectors in it. So just something to watch out for. This wording is really important. In this first example, you're asked to find the null space. So that's the whole thing. So that's going to be the span of the basis. You're going to have infinitely many vectors. In the second example, you're asked to find a basis. And that one little word is really important. It makes a big difference. If you want just the basis, well, then you're going to have a set with a finite number of vectors depending on the dimension of the space, in this case, 2. All right, so that's how you find the null space of a matrix and a basis for the column space.